What if the closest place to alien life in the entire solar system is not a planet, not a distant star system, but a frozen moon smaller than the width of a single country, hiding an entire ocean that has been quietly cooking the chemistry of life in total darkness for billions of years, and we have only just recently figured out how to read the evidence it has been throwing directly into space the whole time? If that single thought stayed with you even for a second, do me a small favor before we go deeper. Hit the like button right now, tap subscribe with the bell turned on. The like button right now, tap subscribe with the bell turned on, and share this video with one person who still believes Earth is the only world that ever mattered. Because what I am about to walk you through genuinely challenges that assumption. And if the bell is already on, drop a quick comment telling me where you are watching from. I read every single one. To understand what just happened, we have to start with the moon itself. About 1.5 billion kilometers away from the sun sits a tiny ball of ice orbiting Saturn at roughly 238,000 kilometers above the planet's cloud tops. For me, I have to start with the moon itself. About 1.5 billion kilometers away from the sun sits a tiny ball of ice orbiting Saturn at roughly 238,000 kilometers above the planet's cloud tops. From the surface of that moon, the banded storms of Saturn would tower over the horizon like a giant striped curtain hanging across the sky. Daylight out there is roughly 1% of what we enjoy here on Earth. The ground temperature sits near negative 200 degrees Celsius. The moon is only about 500 kilometers wide, smaller than the distance across many nations on our own planet. The name of this frozen speck is Enceladus, and by every reasonable assumption ever made by planetary scientists before the year 2004, Enceladus should have been completely dead. Scientists before the year 2004, Enceladus should have been completely dead. Dead. Quiet. Frozen since the day the solar system finished forming more than 4 billion years ago. Just a leftover chunk of ice, slowly drifting in circles around its parent planet, doing nothing in particular. That is exactly what the Cassini spacecraft was told to expect when it arrived at Saturn in the summer of 2004 to begin a long photographic survey of the entire Saturnian family. Cassini was tasked with photographing moons, mapping magnetic fields, weighing atmospheres. It was not sent to search for life. It did not even carry the right instruments to search for life. It did not even carry the right instruments to search for life. It was essentially a geology mission aimed at an outer planet. Designed back in the 1980s and launched in 1997, long before anyone suspected what was hiding in this little ice ball. Then the magnetometer returned, something that made no sense at all. Saturn's magnetic field is enormous. It is one of the strongest fields anywhere in the solar system. Around a small, frozen, geologically quiet moon, that field should simply pass straight by, almost undisturbed, the way wind moves past a stone sitting in a field. Instead, the readings showed the magnetic field, stone sitting in a field. Instead, the readings showed the magnetic field curving, bending, wrapping itself around Enceladus as if it had struck something soft and gaseous. Magnetic fields do not bend around solid ice, they bend around gas. Something was streaming off Enceladus in enough volume to physically push back against the planet-sized magnetic field of Saturn itself. The Cassini mission team rewrote the entire flight plan on the spot and told the spacecraft to swing back lower and faster. All instruments aimed straight at the southern hemisphere of this supposedly dead little moon. What Cassini found was not a dead rock at all. Enceladus was erupting, physically pushed back against the planet-sized magnetic field of Saturn itself. The Cassini mission team rewrote the entire flight plan on the spot and told the spacecraft to swing back lower and faster, all instruments aimed straight at the southern hemisphere of this supposedly dead little moon. What Cassini found was not a dead rock at all. Enceladus was erupting. And over the next 2 decades of careful study, scientists slowly realized that the eruptions were not casual puffs of steam. They were firing the raw chemical ingredients for biology out of the moon's interior at supersonic speed, straight into the vacuum of space, where Cassini happened to be flying through with open instruments. Picture this for a moment. Near the south pole of Enceladus, 4 enormous parallel fractures are cut deep into the icy crust. Each one of those cracks is more than 100 kilometers long and hundreds of meters deep. Astronomers named them after famous ancient desert cities: Alexandria, Cairo, Baghdad, and Damascus. They are nicknamed the Tiger Stripes. Out of those 4 deep canyons, the moon throws towering columns of water vapor, fine ice grains, salts, and gas out into space at speeds approaching 1,300 kilometers per hour. The eruption is so forceful that Enceladus cannot even hold on to its own material. Most of what leaves the surface never falls back down. It escapes entirely. That escaped ice does something stranger still. It spreads out along Enceladus's orbital path and forms a vast, ghostly halo of material around Saturn itself, formerly known as the E ring. One of Saturn's most famous rings is being actively sprayed into existence, moment by moment, by a single tiny moon quietly leaking its own ocean into space. That fact alone carries an enormous implication. You cannot spray liquid water out into space unless you actually have liquid water to begin with. Somewhere beneath that armored icy crust, something has remained liquid for the entire age of the solar system. If that realization has done anything to you, take a breath and stay with me, because scientists have not finished space unless you actually have liquid water. To begin with, somewhere beneath that armored icy crust, something has remained liquid for the entire age of the solar system. If that realization has done anything to you, take a breath and stay with me, because scientists have not finished asking what this ocean actually contains. The plankton-sized world of Enceladus is about to get a lot stranger and weirder, and a whole lot more interesting than what you imagined when you clicked on this video. The next part of the story changed how an entire generation of planetary scientists thinks about life. After the plumes were confirmed, scientists worked for years combining gravity measurements with careful density maps of the cracked crust. The picture that came together was this. Under roughly 20 kilometers of ice, significantly thinner near the South Pole, sits a global ocean of salty liquid water. By global, I do not mean a small underground lake. I mean an ocean that wraps around the entire moon, roughly 10 kilometers deep on average, deeper than Earth's own Mariana Trench at its lowest point. The ice has to be very thin near the South Pole for the geysers to be possible at all, which is exactly why that is the only region of Enceladus with active surface changes. Now the obvious problem emerges. Out at Saturn's distance from the Sun, sunlight delivers only about 1% of the energy it delivers to Earth. It cannot melt anything out there. So what is keeping an entire ocean liquid in one of the coldest regions of the solar system? The answer is one of the strangest pieces of physics in the outer solar system, called tidal heating. Enceladus does not orbit Saturn alone. It is locked into a precise gravitational relationship with a much larger neighboring moon called Dione. For every single orbit Dione completes, Enceladus completes exactly 2. The 2 moons line up in the same configuration over and over again and again, and every time they do, Dione gives Enceladus a measurable gravitational tug. The repeated tugging prevents Enceladus from settling into a clean circular orbit. Instead, its path gets stretched into an ellipse, so the moon ends up perpetually falling towards Saturn, then drifting back out, over and over, billions of years without a break. When it swings close to Saturn, the planet's gravity stretches the entire body of the moon out of shape. When it drifts back out, the moon relaxes. Squeeze, release, for billions of years. Deep inside Enceladus, in the rocky core at its center, all that constant. Inside Enceladus, in the rocky core at its center, all that constant. Flexing grinds rock against itself, generates friction, and that friction does exactly what friction always does. It produces heat. Astronomers call this tidal heating, and in Enceladus, it works like a permanent internal furnace, melting ice from beneath and keeping an entire global ocean alive in total darkness. The implications of this single physics effect reach far beyond Enceladus itself. Before tidal heating was confirmed by Cassini, scientists assumed that liquid water on a world meant it had to sit at the right distance from its star. Once tidal heating proved it could keep an entire... The implications of this single physics effect reach far beyond Enceladus itself. Before tidal heating was confirmed by Cassini, scientists assumed that liquid water on a world meant it had to sit at the right distance from its star. Once tidal heating proved it could keep an entire ocean liquid this far out in the cold, that map of habitability changed forever. Any icy moon locked into the right gravitational rhythm with a larger partner became a candidate, regardless of how cold and dark its home turned out to be. Europa at Jupiter works through a similar mechanism. So does Titan in its own way. Enceladus simply happened to be the one that handed us direct proof, sprayed into space, where a passing spacecraft could actually catch it. But an ocean alone is just water, and water is only the beginning. The real question to be the one that handed us direct proof, sprayed into space, where a passing spacecraft could actually catch it. But an ocean alone is just water, and water is only the beginning. The real question has always been what is dissolved inside it. For years after the plumes were discovered, the best answers came from Cassini's dust analyzer sampling ice grains as the spacecraft flew directly through the plume. Those early readings returned organic compounds. In 2018, larger complex carbon-based molecules showed up as well, but there was always a nagging doubt. Grains drifting out in the E-ring can spend anywhere from months to centuries floating through one of the most punishing radiation environments in the outer solar system. Those particular molecules could theoretically have been manufactured by radiation exposure in space long after they had left the moon, with nothing to do with the actual ocean. So researchers went back and pulled up a measurement from an older, much faster, much closer flyby. On October 9th, 2008, Cassini made its deepest dive, flying directly through the geyser plume at just 25 kilometers above the icy surface, moving at nearly 18 kilometers every single second. The ice grains it sampled that day had just left the ocean minutes earlier. At that age, meaningful radiation damage is essentially impossible. A second scientific advantage came from the speed of the impact itself. At slower impact speeds, water molecules tend to survive in clusters that smother the underlying chemical signal, almost like a curtain drawn across the data. Only at that extreme velocity did the curtain finally tear open enough to see clearly. The full reanalysis of those data, published in October of 2025, revealed molecules inside freshly ejected ice grains that simply had not been detected in any ocean beyond Earth before. Alongside the ring-shaped aromatic compounds already known from earlier work, the team identified aliphatic chains, esters, alkenes, ethers, and tentative signatures of nitrogen and oxygen-bearing molecules. Esters and ethers in particular matter more than they sound at first. They are essentially chemical connectors, the joints that allow simple carbon-based molecules to link together and assemble into far more complicated ones. And with that 2025 finding, the lingering ambiguity was finally gone. This chemistry was not manufactured by radiation exposure out in space. It was made somewhere inside the moon itself. To understand what could possibly be manufacturing molecules like those beneath 20 kilometers of solid ice, researchers paused for a moment and started looking at the floor of our own ocean instead. A few kilometers beneath the surface of the Atlantic, sitting in permanent darkness, Earth's crust cracks open in certain places. Superheated mineral-rich fluid pours out of towering rock chimneys and slams directly into near-freezing seawater. That violent meeting drives a chemical reaction called serpentinization. Iron and magnesium-rich rock reacts with water, releasing three things in the process: heat, hydrogen gas, and the precise kinds of complex carbon-based molecules that Cassini pulled out of the plumes at Saturn. Around vents exactly like these here on Earth, life does not merely survive. It actively crowds in tube worms, thick mats of bacteria, whole self-sustaining ecosystems that never see a single ray of sunlight and have no need to, because they run on raw chemistry instead of light. Cassini detected molecular hydrogen streaming directly out of Enceladus, on the floor of our own ocean. That same hydrogen serves as food. It sits at the very bottom of an entire food chain. What makes this comparison so compelling to researchers is not just that the chemistry looks similar on paper. It is that we already have living proof of the concept working right here at home in an environment that used to be written off as equally hostile. For a long time, deep-sea vents on Earth were assumed to be lifeless, simply because nobody imagined an ecosystem could function without sunlight anywhere near the base of its food chain. That assumption turned out to be wrong the moment researchers actually sent a submersible down to look. Enceladus is essentially asking scientists to make that same leap of imagination a second time, just considerably farther from home. If this ocean story has been even half as gripping to you as it is to me, do this one small thing. Comment the words, "Send Cassini home" right below this video, because I want to know how many people watching right now would actually be willing to see humanity go and land on that erupting ice. I will read every single reply, and the ones that catch my attention often end up shaping the next video I make. It also tells the algorithm this story is worth more people's time, and that alone helps the channel reach someone who has never heard the name Enceladus before today. To compare the case for life at Enceladus to anything else, astrobiologists use a simple checklist known by the acronym CNOPS, standing for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those 6 elements make up essentially every living thing we have ever examined on Earth. Cassini found the first 4 without much difficulty. Phosphorus, though, refused to show up for years. That absence genuinely mattered. Phosphorus forms the structural spine of the DNA double helix, and it sits right at the center of ATP, the molecule every single living cell on our planet uses to move energy around inside itself. Without it, you can have plenty of interesting chemistry. You simply cannot have biology the way we understand it. For a long stretch of time, the missing phosphorus was treated as a serious problem. Researchers could point to warmth, water, and organic carbon all they wanted. But without phosphorus specifically, the entire case for Enceladus remained incomplete in a fairly fundamental way. Some scientists even started to wonder whether phosphorus might simply be locked up too tightly in the rocky core of Enceladus to ever make it into the ocean water at all, which would have quietly closed the door. That answer finally arrived in 2023, 6 whole years after the Cassini spacecraft had already been deliberately destroyed by mission controllers. A research team went back through archived dust readings from the E-ring and found unmistakable signatures of dissolved phosphates, sitting at concentrations at least 100 times richer than anything found in Earth's own ocean. Every single letter on the CNOPS checklist was now accounted for. Not inferred from indirect evidence, not estimated. Genuinely measured directly from ice that had only just left the moon. That discovery, published in the journal Nature, left one final assumption still untested. Having the right ingredients sitting on the shelf is not the same thing as actually being able to cook with them. So in 2025, research teams in Japan and Germany set out to rebuild Enceladus's entire ocean on a laboratory bench. They recreated the pressures, the temperatures, the mineral chemistry, and the underlying hydrothermal reactions, then simply let the system run. The resulting reactions produced a wide range of complex organic molecules, including aldehydes, nitriles, and even amino acids. The freezing process itself helped generate simple amino acids like glycine along the way. Many of the compounds produced in the lab matched what Cassini had originally measured out at Saturn almost exactly. Take a real moment to sit with that. A chemical recipe originally written on another world was successfully reproduced, right here on our own, and it genuinely works. Amino acids are what proteins are built from. Proteins are what cells are built from. Enceladus is not just a place where life might become possible someday in some distant future. It is a place where the chemistry that comes directly before life has already been demonstrated to run entirely on its own, with no outside help required. And none of this is ancient history sitting in the past. In 2023, the James Webb Space Telescope stared directly at Enceladus's south pole and recorded a single, continuous jet of water vapor stretching more than 9,600 kilometers out into space, nearly 20 times longer than the entire moon that produced it. Webb measured the actual output at roughly 300 liters of water escaping every single second, continuously. That internal furnace is not some distant memory. It is actively burning right now at this very moment while you have been watching this video. More recent work has only added to the picture. A reanalysis published in 2024, examining Cassini's original gas measurements, turned up hydrogen cyanide along with acetylene, propylene, and ethane. Hydrogen cyanide happens to be toxic to humans and to plenty of other organisms on Earth, but it is also directly relevant to the earliest chemistry believed to precede life. Laboratory reactions involving it can produce both amino acids and the basic components of nucleic acids. Some researchers have started calling it a Swiss Army knife molecule for building the very first chemical precursors to biology. The same study found evidence for genuinely diverse oxidation and reduction chemistry that could support multiple different energy pathways at once, not just one. And in May of this year, a separate team announced they had identified a hidden chemical signature technique that could one day help detect genuine biological activity directly within plumes like these, adding yet another tool to a growing toolkit aimed squarely at one small moon. Taken all together, the individual findings stack into something far more persuasive than any single result on its own could manage. Liquid water alone would be interesting. Organic molecules alone would be interesting. Phosphorus alone would be interesting. It is the fact that every single item on the habitability checklist keeps showing up, one after another, from the same tiny moon, that has genuinely shifted how seriously the scientific community now treats this particular target. None of this proves that organisms are actually living down there, and researchers are careful to say so themselves. Finding the right ingredients removes an obstacle. It does not confirm a conclusion. But it brings us directly to the obvious next question people keep asking. If this ocean is warm, salty, chemically loaded, and actively cooking organic molecules, why did Cassini not simply go ahead and find life directly? The answer to that question is not about astronomy at all. It is about engineering. Cassini was designed in the 1980s and launched in 1997, years before anyone even knew Enceladus had an ocean, let alone an active plume. Its job was to weigh molecules, chart magnetic fields, and map terrain in broad strokes. It carried no microscope on board. It had no instrument capable of sequencing genetic material, and no way to recognize something as simple as a cell wall on the spot. Cassini did not somehow miss alien life sitting right in front of it. We simply never gave the spacecraft the ability to look for life in the first place. It was sent out to look for smoke, and it ended up finding smoke pouring steadily out of every single crack in the ice. Every major breakthrough in this entire story so far has been an act of rereading, not of discovering for the first time. Genuinely new answers squeezed out of information that had been sitting quietly in archives for years, waiting for someone to finally ask the right question. And here's the part almost nobody knows about yet. In late 2025, after a long process stretching back through several years of planning, the European Space Agency formally committed to its single largest dedicated science funding commitment in recent memory. Buried inside that decision was a specific target: Enceladus itself. The mission has been designated L4, and it stands as the very first flagship mission of Europe's broader Voyage 2050 program. This is planned as a full orbiter carrying a dedicated lander along with it. Current planning has it launching sometime around 2042 and arriving in the Saturn system sometime in the early 2050s. It will sample the plume directly from orbit first, then eventually set a spacecraft down on the erupting terrain near the South Pole. Weeks of direct surface operations in conditions no human probe has ever faced before. If you have watched this far and you want to keep the story alive in your feed, do not leave without tapping subscribe and turning the bell on, because the next major breakthrough on this moon is almost certainly already sitting inside some archive somewhere, quietly waiting for someone to notice. Channels like this one only survive when people who care about this kind of story choose to keep it going. You're literally one click away from making sure that happens. And the alert on your phone when the next update drops is going to be one of the most exciting notifications you get all week. Committing that level of funding this far in advance is genuinely unusual, even by the standards of planetary science, a field already famous for thinking in decades rather than years. It tells you something about how seriously the underlying data has been taken behind closed doors long before the general public ever heard anyone say the word Enceladus outside a documentary. Building an entirely new generation of instruments specifically designed to detect biological activity directly, rather than just inferring habitability from chemistry, is not something that can be rushed. It has to start now if it is going to be ready when the narrow launch window opens roughly 17 years from now. The launch window itself is dictated directly by orbital mechanics, including a specific sunlight angle needed at the South Pole once the spacecraft actually arrives. Miss that window, and the next real opportunity slips away by decades. That is exactly why the technology is being funded right now, a full 17 years before anything actually leaves the ground. So here is where things genuinely stand today. A global ocean of liquid water, a permanent internal heat source keeping it that way, a rocky seafloor actively exhaling hydrogen, phosphates, aromatic compounds, esters, and ethers. A laboratory experiment here on Earth that has now proven this exact chemical recipe genuinely assembles itself on its own, with no living thing involved. Everything is in place except one single missing piece, a machine specifically built to actually go look. That machine now exists on paper, complete with a chosen landing site, and an actual date circled on the calendar. For the very first time in human history, we are not simply asking whether we could go look for life on another world. We are genuinely counting down toward actually doing it. And every single answer this small moon has given us so far came from data we already had, sitting quietly in our own archives, sometimes for years, before anyone thought to look at it the right way. If something inside you wanted this story to keep moving when the next piece of news hits, hit that subscribe button one more time right now, turn on every notification, and share this video with the curious friend you have been meaning to send something interesting to all week. Because the next chapter of this story is being written right now in laboratories, in mission control rooms, and inside instruments that do not even fully exist yet. And when the next headline drops, I want to be one of the first places you hear about it, not the last. The next chapter of finding out whether we are alone is no longer theory. It is a countdown, and you are standing right at the front of the line.